Okay, so today we will discuss about chapter 2, right? So for chapter 2, this chapter is called atomic structure. So this is some of the checklists, all right, of the expected learning outcome that you need to know at the end of the chapter, all right? So you can use this checklist to counter check whether you have mastered all the necessary concepts in that particular chapter or not. Okay, we need to be able to differentiate atom, molecules, and also ion. All right, so we just need a very basic method to differentiate atoms, molecules, and ion. Okay, we don't need to memorize all the long definition at the moment. All right, we need a very simple keywords or a simple idea for this differentiation. Okay, for example, okay, so when the questions say about particles, okay, whenever they got particles, we have three possibilities. The first particle is called atom. The second particle is called molecules. Meanwhile, the third particle is called ions. Alright, so for these three particles, so you should be able to differentiate them by using some of the key idea. Alright, so for atom is actually any particles that come alone. So if the particles only come by one, that is called atoms. Alright, we're going to do three examples here. So the first example, it can be a carbon. So carbon only come alone, so it is an atom. Alright, now we have aluminium. So aluminium also come alone, you only see there's one atoms over here, so this one part under atoms. So we also can have a zinc, Zn. So zinc also come alone, alright, it doesn't combine with any other things. Okay, you only have one quantity here, so it is atom. Alright, meanwhile, for molecules, we are looking for a gang, right? We are looking for gang of non-metals, alright? So the word gangs means that it must be a combination. It doesn't come alone, right? So when you have a non-metal and non-metal adjoining together, you are going to get molecules. Alright, so we're going to do three examples as well. This example is that, alright, so we have a carbon dioxide. So carbon dioxide is made from a non-metal carbon and a non-metal oxygen. So when you have non-metal and non-metal, this is molecules. So another one more example, we can have water. So water is made from the non-metal hydrogen and non-metal oxygen. So when non-metal and non-metal are joining together, this is molecules. Alright, one more example, maybe a bit lengthy, but the concept is the same. So we have ethanol. We have ethanol, which is one of the alcohol. So ethanol form hydrogen and oxygen, which are all non-metal. So when we have non-metal gangs or non-metal substance add together, this guy is called molecules. Alright, lastly, so another type of particle is called ion. So ion have two different ways to differentiate it. Okay, number one, ion can be anything that got charge. Any particle that carry charge, it's called ion. Alright, for example, so let's say I was given Al3 positive. So I see a charge over here, so this is an ion. Let's say I have Zn2 positive. So this particle carry charge, it's ion. Alright, sometimes the charge might be hidden. For example, we have sodium chloride. For this particle, we don't see any charge written on the formula. So a lot of people will thought this might not be the ion, since the ion has to, own the charge. Alright, so this particle actually has the charge. It's just that it is being hidden. Na is Na positive, Cl negative. Because of positive and negative, the charge cancel out. So it's not to say that the charge is not there. It's just that the charge is being cancelled out. The charge is hidden. So how are we going to differentiate this is ion, since sometimes the charge might be hidden? Alright, that's why we have two criteria to know what is ion. Number one, ion is something got charge, or ion is anything that made from metal adjoining with non-metal. Alright, so for example, sodium is a metal, chlorine is a non-metal. Metal join together, so we will get ions. Alright, alright, so after we all learn the difference between three types of particles, so let us try to put it into practice. So first of all, please refer to the exercise booklet. Alright, please turn on to page number 5. Okay, turn on to page number 5. Alright, so for page number 5, we will try to do the questions together. So the first questions that we will do is on question number 2. Alright, so you can refer to question number 2. Okay, so for question number 2, this is the SPM past year, this came out 2017. The question asks which of the following pair is actually matched in a correct manner. Alright, so first of all, we will try to come up with all the formula. Ammonia formula is N. So ammonia is made from nitrogen, which is a non-metal, and hydrogen, which is a non-metal. When non-metal adjoining with non-metal, so it is a molecule. So the answer A should be correct. Anyway, let us look at answer B to donkey to understand why they are incorrect. Okay, for the second answer, neon. Neon has a formula of Ne. As we can see, N and E cannot be. N and E is considered as only one atoms. Okay, only one species or one particle that come alone. So when neon come alone, it should be atom. Okay, the next one we have nitrogen dioxide. Nitrogen is N, dioxide is O2. So nitrogen dioxide is made from nitrogen and oxygen, which both of them are non-metal. So when we have non, should be molecules. Okay, lastly we have hydrogen chloride. Hydrogen chloride formula is written as HCl. So HCl is made from a non-metal H and non-metal Cl. So non-metal H and non-metal Cl, you're gonna get a molecules. Okay, all right, we will try to do another one more questions. Okay, so now let's looking on question number 3. Ion is something that got charge, or ion is something that made from metal adjoining with non-metal. Alright, so now let us try to figure out the formula. Answer A, carbon dioxide, CO2. Carbon dioxide is made from a non-metal carbon and non-metal oxygen, so it is a molecules. Alright, answer B is SO2. SO2 is made from a non-metal sulfur and oxygen. Again, it should be a molecules. Answer C, calcium chloride. Calcium chloride formula CaCl3. Calcium chloride CaCl3 is made from a metal calcium and a non-metal chlorine. So metal, non-metal, it should be ion. Answer donkey, we have Cl. Hydrogen chloride consists of hydrogen and chlorine. Both of them are non-metals. So when we have non-metal and non-metal adjoining together, again it is a molecules. Okay, all right, so I hope now you have some idea, okay, for our first objective, which is differentiate atoms, molecules, and ion. Remember, atom is a particle, molecule is a particle whereby non-metal join with non-metal. Ion is those particles that got charged or a metal adjoining with non-metal. Okay, so Now we will look on to the second objective. The second objective is that we must be able to differentiate elements and also compound. Alright, so element different than atoms, molecules and ion. Alright, okay. So first of all, we have to know what is element and what is compound. So element is anything that is formed by only one species, or in the other word, it only formed by one type of atom. So when we only have one type of atom, or in short one species, that is an element. Alright, for example, okay, carbon is made by only one species, so it is an element. Alright, zinc is made by one species, it is an element. Alright, so now we try to use some example that sounds and looks a little bit more confusing. Right now we have oxygen, O2. So oxygen is O2. First of all, a lot of students are getting confused by number 2 here. So although you have 2 oxygen, it doesn't mean that you have 2 species, because both of the O, they belong to one same species. So we only have one species here, which is O, that repeated for 2 times. So in this case, we only have one species out there. So this is still elements. Same as 8. Again, we shouldn't get confused by the number 8. So although we have 8 sulfur, but all the sulfur considered as one species. Alright? So in this case, this is still elements. Alright. So in contrast, compound. Compound is anything formed by more than one species. Anything formed by more than one species, okay? Or anything formed by more than one elements. Alright? So then you will get something called a compound. Alright, for example, so we have a carbon dioxide. Carbon dioxide is made from carbon, which is one species, and oxygen, which is another species. So there are 2 species over here, so this is a compound. Let's say we have a methane, CH4. Methane is made from a carbon, which is one species, and hydrogen, which is another species. So when we have more than one species in this particular substance, so this is a compound. Alright? So as usual, we will try to practice on the actual apply all the concepts that we have learned. Alright? So we turn back to the page number 5, the same page as just now. Alright, now let's look at our first question. Okay? So this is a question came out in SPM 2008. So the question is asking which substance is actually an element. So again, when you see the word element, you should think about this thing in your mind, which is called one. Looking for something that got one species only. So the first A, the answer is air. So air. So we should know that in air, there consists of many different gases, such as nitrogen, oxygen, helium, argon. So there are many species in the air. So when you have more than one species, it shouldn't be. Alright. So B, we have steam. Steam is of H2O. So H2O made from a H and O, which are 2 different species. So it is a compound. For answer C, we have carbon. Carbon formula is C. So we only have one species over here. So carbon supposed to be the elements. Okay? So I hope we learned today. So all of you be able to differentiate a difference and distinguish the difference between elements and compound. Remember, elements is anything formed by one species. Compound is anything formed by more than one species. Okay? So this is how we differentiate elements as well as compound. Alright, so now we will get into part 3. Okay, part 3, we will learn how to predict state of matter. Okay, what it means by predict state of matter. Okay, first of all, we have to understand what it means by state of matter. Alright, when you see state of matter, matter normally can exist in 3 forms. So which is called a solid, which is called a liquid, and also a gas. Alright, so whenever we see the word state, we must think about solid, liquid, or a gas. Okay, so in SPM, okay, in SPM, they love to give us a question like this. Okay, so the question will always given us the melting point. Alright, the question will give us a melting point. The question might given us the boiling point. So when they given us the melting and boiling point, so the question will ask us to predict the state. Okay, predict whether that substance would be a solid, a liquid, or a gas at a very specific temperature. Okay, so this specific temperature they will mention of the time. Alright, they will mention most of the time, but sometimes, okay, they love to use a term that we all have to be very careful. One of the terms they love to use is this. It's called room temperature. Okay, so all of you must be very careful and you must be alert with what is the values of room temperature. Okay, so in chemistry, room temperature, it's always denoted as 25 degrees Celsius. Okay, so you have to be very careful on this, because sometimes a lot of people thought the temperature 37. 37 is not the room temperature, but is actually the human body temperature. So I repeat one more time, room temperature is always referring to 25 degrees Celsius. Alright, so how are we going to do questions like this? Okay, we will try to use an example for demonstration. So let's say we are given a simple example. Example was saying that, alright, I have a substance called X. So substance X, the melting point is given to us. Let's say the melting point degree Celsius. Alright, the boiling point is also given to us. Let's say the boiling point is 180 degrees Celsius. So the question asks us to predict the states, alright, of X. So we need to predict the state of X at a specific temperature. Let's say the specific temperature is 30 degrees Celsius. So if you want to solve a question like this, alright, there's a few methods. One that we all can employ is a method, we call it as 3 lines method. Alright, so 3 lines method, as the name indicates, so we need to draw 3 lines. So the first line would be a horizontal line. After that, there will be 2 vertical lines. So you will see that 1 horizontal and 2 vertical line has total 3 lines in total. These 3 lines will make 2 intersecting points. The first intersecting point here must be a melting point. Meanwhile, the second intersecting point would be boiling point. Alright, so now we need to fill in 3 letters in the box. Alright, the first box on the left here is called S. S stands for solid. The second box in the middle is L, which stands for liquid. The last box on the right hand side here is a G, which we call a gas. Alright, so what we need to do is this. So whenever we want to predict the states of matter, first of all, you fill in the melting and boiling point as per given in the question. Alright, so as per given in the question, the melting point is 70 and the boiling point is 180. So let's put it in. So our melting point would be 70 degrees Celsius. Our boiling point is 180 degrees Celsius. So what is the temperature that they are interested for Celsius? So at here, we just need to use a concept of mathematics which is called number line to figure out the locations of 30 degrees Celsius. So if you look at the number line here, 30 degrees Celsius, 30 should be somewhere below 70. So 30 should be somewhere on the left. So I shape this region. So I know this substance X should be a solid at 30 degrees Celsius. So my final answer is a solid. Alright? So I hope you get some idea. It's not a very hard concept. Okay, we will try to practice, try to figure out or try to do tunes on this. Okay, hopefully it will increase your understanding. Okay, so first of all, refer back to the exercise booklet. Alright, so for the exercise booklet, now we will look at our page number 6. Alright, so now turn on to another one more page. Okay, so now we turn on to page number 8. Okay, we turn on to page number 8. So for page number 8, look at the first question. Okay, so the first question is a SPM 2012. So the question gives us a table. So the table gives us the melting and boiling point for 4 different substances, which is called V, W, X, and Y. For each of the substances, the boiling point and the melting point are given. Alright, so now the question asking us which substance is a liquid at 100. Whenever we give a melting point, boiling point, we want to play with the states, solid, liquid, and gases. So we know 3 lines method can come in. Alright, here we need to understand a concept because this question will employ a bit on the K-bar concept. Alright, so according to 3 line methods, okay, according to 3 line methods, we all know the first intersection is melting point. And we all know that the second intersection should be boiling point. The first boxes on the left is a solid, the second box should be a liquid and liquid. Okay, we want the substance to be a liquid at 100 degrees Celsius. So if you want to be liquid at 100 degrees Celsius, the liquid is somewhere in the middle. Alright, so we want a liquid at 100 degrees Celsius. So if you want to be liquid in 100 degrees Celsius, this 100 degrees Celsius must be placed in between the melting point and in between the boiling point. Alright, so we must choose a melting point and a boiling point combination in which the 100 degrees Celsius is in between them. Okay, so if we look at the answer, alright, the first one is 200, 600 is obviously not in the middle. 100 is somewhere toward here. Alright, so the second answer, 170 and also 150. As same thing, the 100 shouldn't be in the middle, the 100 should be somewhere over here, so which is not a liquid. For the answer C, we have 130 and 80, and 100 is in the middle of the 80 and 130. So when the 100 is in the middle of the melting and boiling point, it is a liquid. So I think my best answer go for X, which is C. Alright, we will try to do another. So the subsequent question, this is a SPM 2009. Alright, so this question is very similar as the questions like what we saw a moment ago. Alright, so we still given 4 substances, we still given their corresponding melting point and boiling point. So the question asks which substance is a liquid at room temperature, is referring to 25 degrees Celsius. So we will play with the concept. So if we want a liquid at room temperature, if we want a liquid, so we need the box in the middle, the liquid. Alright, so we know that to be liquid, this room temperature 25 degrees Celsius must be in between the melting point and in between the boiling point. So our answer we must find a concept in which the 25 is sandwiched in between melting and boiling. For answer W, 25 is not in the middle of -157 and -9. That's why it's wrong. For answer X, 25 is in the middle of -13 and 55. So it's okay. For answer Y, 25 is not in the middle of 80 and 196. It should be somewhere here. For answer Z, 25 is not in the middle of 200, be less than 256, should be somewhere here. Alright, so to be liquid, we 25 to be in the middle, to sandwich between melting and boiling point. That's why our best answer go for Y, which is C. Alright, so I hope for now you already get some idea, okay, how are we going to predict the states of matter, let it be a solid, as when you given a melting and boiling point. Alright, so this is our third objective. Alright, so next on we will discuss for our fourth subtopics, which is diffusions, okay, or we also can call it kinetic theory of matter. Right, so first of all, we have to understand that diffusions and kinetic theory of metals is always come out at the same time, which means that if you are given a diffusion questions, okay, you can always use kinetic theory of matter to explain. Alright, so this is something that you have to bear in mind. So first of all, we have to understand kinetic theory of matter. So for kinetic theory of matter, alright, basically there are three main concepts that we need to know. Okay, the first concept is that we have to know that all the matter or all the substance, chemical substance, it's always formed by some tiny and also discrete particles. Okay, matter always formed by some smaller building particles. Alright, secondly, we have to know the particles always have a form of movement, no matter it's vibration, rotations, or it's a real movement. Alright, so the particles, it always move randomly. Okay, particle always they move randomly. Alright, the third one, although particle moves randomly, but there is always a directions, or there is always a trend for them to move. So when the particle want to move, the particles normally always move from a high concentration region all the way to a low concentration region. So particles always move from a place crowded to a place which is less crowded. So this is the kinetic theory of matter. And do remember, okay, we will always use, alright, kinetic theory of matter. Alright, we always use kinetic theory of matter in order to explain one of the phenomenon. Alright, this phenomenon is actually called diffusion. Okay, we call it a diffusion. So in some of the questions, sometimes they don't use the word diffusions. Alright, so sometimes they will twist and turn the questions a bit, so we have to be very, very careful. Okay, so there are a few keywords that is enable us, that help us to figure out that it is actually a diffusions. Alright, so one of the keyword we can look around is called mix. After that, we also can look at some of the keyword called spread, alright, disperse, or some keywords like move. Alright, so these are the keywords that actually give you some idea that the questions is actually playing around with the diffusion concept, in which you can employ kinetic theory of matter to do the explanation. Alright, so let us handpick a few questions in the exercise booklet to discuss, so that we concepts. Okay, so first of all, we can turn on number 6. Alright, so this is page number 6. Alright, so for page number 6, we will try to look at the first question. Okay, so this question is actually SPM 2005. Alright, So the question is actually given us a diagram. So as we can see on the left hand side, colors in the beginning. At the bottom here, we put a copper 2-sulfate, which is a blue color solid. So after a few days, you can see that the whole colorless region, the whole thing actually become blue. So what we can see is this. Initially, the blue color was centralized on a locations or a certain position. But after a few days, you can see the blue color go and fill up agar. In the other word, the blue color is actually spread, move throughout the whole gel and jelly. Alright. So here when you see there's a process of spread, or when you see the blue color is actually moving. Alright. So we know that this is actually a diffusion concept. Alright. So now this question was asking us which of the following is the best action. So we have to be careful with this kind of question. When they ask us best action, which means that the answer might have a few answers which is correct, but we have to choose the best one. Okay, we have to choose the best answer to explain our observation. So our answer A is saying that agar dissolve copper 2-sulfate. Alright, so when we are playing with diffusion concept of dissolve, alright, we more like the word make, spread, moving. Alright, so look at B. For B, the question say that copper 2-sulfate is ionic compound. Nothing wrong. Actually, this statement is correct, but it's not suitable to explain diffusion, because diffusion has nothing to do whether you are ionic compound or covalent compound. So it's wrong. So for C, the question say that the particles in copper 2-sulfate are minute and discrete. Minute means very, very tiny. Alright, so you have some tiny and very discrete particle, which is true, because we know when it comes to diffusion, we can use a kinetic theory of matter. So for kinetic theory of matter, one matter is formed by tiny and discrete particles. Alright, so I would say that the answer C is correct. Okay, our answer donkey, the attractive force between agar and copper 2-sulfate particles is strong. Okay, so when we want to play around with diffusion, when we want to play around with kinetic theory of matter, so we are not really interested. Okay, so the best answer would go for C. Alright, we will try to discuss one more objective questions. Alright, so this is question number 5. This is a question that came out in SPM 2009. So the question say the following statement are about diffusion. So they clearly tell us that this is a diffusion. So first statement saying that, alright, we have tiny particles and they are fixed. The second statement saying that randomly. Alright, so if we check, actually all these things, alright, it's tally with our kinetic theory of matter. Okay, alright, now, so which of the following situation are explained by the statement above? So you want to refer to situation. So remember, when you come to diffusion, what is our main concept? Mixing, we are looking for a process of spreading, we are looking for some sort of movement. Alright, so these are some key ideas we are looking at. Alright, so for answer number 1, bromine gas mixed with air. The mix, it is about diffusion. Okay, alright. For the second answer, aqueous copper 2-sulfate moving through a gel. Moving, move is also profusion. For answer number 3, we have melting. Melting has to do with diffusion, because please remember, diffusion is all about a process of moving or mixing or spreading. So melting is not in. Alright, lastly, alright, we turn to the next page. Okay, so the last answer, combustions of magnesium in air. Combustion means burning. Burning has nothing to do with diffusion. Our answer that is acceptable would be the first one and 1 and 2. So the answer 1 and 2. So it's A. Alright. So we will try to do one more questions together. So now these questions has a little bit different in the format. So now we are trying to do a subjective questions. Okay. Alright. So this question saying that diagram 3.1 shows the result of experiment to invest bromine particles in air. So you see the movement, we can make a wild guess, is actually a diffusion concept. Alright, so now we can see, alright, we have a bromine vapor here, and here this is air, which is colorless and empty in the beginning. Once the cover being removed, you can see that the whole thing become brown color, which means that the brown color is dispersed. Alright, so the first question is asking us to name the process experiment. So when you see a process of disperse, spreading, mixing, we all know this is diffusion. Alright, so second question is related with what we learned early on today. Alright, so the second question asks us to mention what is the type of particles in the bromine gas. So remember, whenever you see the word particle, there's only three possibilities. It might be a molecules, or it might be ion. So remember how we differentiate them. Atoms is something who come alone. So bromine have Br2, there are two bromine over there. So it's not alone, obviously it's not atoms. Alright. Molecule is a non-metal adjoining with non-metal. So bromine is a non-metal adjoining with another bromine, which is also non-metal. It should be a molecules. Why it couldn't be ion? Alright, because in order to be ion, number one, you might have charge, which we don't see any charge over here. Or ion can also be a metal combined with non-metal. So we don't have any metal in the bromine, so it cannot be ion. So the best answer should be molecules. Alright, so for the third questions, the question is asking us to explain the observation, explain what we saw in the experiment by using kinetic theory. So we are awarded 3 marks in this question, so which means that we have to write at least 3 points. So do remember, kinetic theory of matter mentioned about 3 concepts. The first concept is actually the matter is actually formed by tiny and discrete particles. Okay. Second statement say that the particles is in a random way. So the particles is moved randomly. So moving in a random way, there are certain direction they always go toward it. So particles normally move, alright, from the high concentration, alright. So particle always move from high concentration area to the low concentration area. Okay, how the particle move. Alright. In SPM, the question asks us a diffusions, alright, that we need to use a kinetic theory of matter to explain, especially in structure questions or essay question, which we need to write. So we need to make our answer as detailed as possible. So actually we just need to, alright, we can use this answer all the time when asking us to explain using kinetic theory of matter. The only thing you need to change here is the word matter. Alright, matter is a very general word, so we have to change and make the word matter fit with our question. So in this case, the substance that actually undergo diffusion, so it's actually the bromine vapor. So bromine vapor is actually the substance that spread. So you just change the matter, become bromine vapor, and the rest of the answer you can just copy and use the template like this. Okay, so asking us if this experiment is being repeated, temperature, so we have to make a prediction. What is the time taken now for the bromine vapor to spread, okay, throughout the whole gas chart? So first of all, we look at any informations that we know about the time for the bromine to spread. So the question telling us initially the bromine should take about 10 minutes to spread. So the question do not mention any specific temperature, alright, so normally it's room temperature. Okay, so now when this experiment is repeated at a higher temperature, so what happened to the time? So we have to understand that temperature is always related, which is called kinetic energy. All right, so the concept, so when we have higher temperature, theoretically all the particles will become more energetic. They have more kinetic energy. So when particle has more kinetic energy, so they will move faster. So when they move faster, the process of spreading, mixing, so when the diffusion process go faster, technical time you need should be shorter. So do not make a wild guess of a time like 5 minutes, 6 minutes, 3 minutes, unless you are very sure how to get the number. Alright, so in this case we have no idea what are the actual time that we need, but one thing for sure, this process will happen faster, the time will be shorter. So we keep in a range or in a margin, we just write less than 10 minutes. Alright, so we know that the diffusion will happen faster at a higher temperature, so the time you needed should be a bit shorter, which is less than 10 minutes. Alright, right, so we have covered diffusions and also kinetic theory of matter. Okay, so going on to the fifth objective. So this concept will be a bit tricky. Okay, it's a bit lengthy. So now we will go into something called heating curve and also cooling curve. Okay, so first of all, we have to understand what heating curve and cooling curve do for us. Alright, so heating curve, alright, and also cooling curve, basically they help us to determine those specific temperature when you change a states. Heating curve is a curve that it can help us to find out our melting point as well as boiling point. Meanwhile, cooling curve is a curve that helps us to determine, okay, the freezing point and also condensation point. Alright, so now first of all we have to be able to identify the shapes of the heating curve and also cooling curve. Okay, no matter heating curve or cooling curve, the shape is that you will see the shape looks like a staircase. Alright, you're going to see a shape like staircase. Alright, so let's start with heating curve. So for heating curve, you will see a staircase like this. So curve is actually a plot of temperature versus the time. Alright, temperature versus the time. So heating curve, you will see a staircase and the staircase is going up. Alright, so you're going to see like up, flat and up. So this is called a staircase. Alright, so why is actually going up? Because when we do heating, the temperature should increase. That's why the staircase is going up. Alright, so normally you will see one staircase, or maximum you only see two staircases. Alright, you are not getting more than two staircases. Alright, maximum is only two. Curve. So if let's say for cooling curve, the shape is still a staircase. The only difference is that for cooling curve, the staircase is actually descending. So you're going to see something like this: down, flat, and down. Alright, so this is for a cooling curve. Alright, so first and foremost, you must be able to recognize what is the shapes of the heating curve and what is the shapes of your cooling curve. Alright, so now after understand the shapes of heating curve and cooling curve, we must know what is happening. So there are two words to study this graph. Alright, so we must be able to analyze. Okay, we must be able to analyze our heating curve and cooling curve. The first thing is that we should be able to analyze what are the states of matter, alright, at every specific region. Okay, state of matter at every specific region. Okay, I give you a simple example. Let's say we use a heating curve. We start with heating curve first. Alright, so for heating curve, we have a staircase going up, and flat. Do remember, heating curve, you should start not from 0, okay, because normally in experiment we start our heating room temperature. So normally our starting point is room temperature, which is 25 degrees Celsius. So we are not starting from 0. That's wrong. Okay, so if we have two staircases, it will be very easy, because on the horizontal portion, that is where they change the states. Okay, so horizontal portions or horizontal region is where we all change states. Change states means that it can be melting, boiling, condensation, freezing. All these called change of states. Alright, so if we have a heating curve, if they have two staircases, then it will be quite easy, because the first staircases will be melting and then the second staircases will be boiling. Simple as that. But if the question only give us one staircase, then we have to be very careful. Alright, if the question give us one staircase, this staircase might be a melting or might be a boiling. Alright, so how are we going to know whether it's a melting or it's a boiling? So in this case, when we only have one staircase, okay, alright, you very careful with, okay, we must know what is our initial states, what is the starting states. Example, if the question say that this thing begins with solid, so you think, so when we have solid and we heated, the first change of states here should be a melting. Alright, meanwhile, if this question mentioned that they give us one staircase and they mention that we begins with liquid, okay, when we first started with liquid, okay, alright, the liquid, the first change of states for liquid should be boiling. Okay, no way liquid will do melting, because liquid is already melted. Alright, so if you have liquid, if you heat it up, the change of state should be boiling. If you have solid, when you heat it up, the change of state should be melting. Alright, so you have to be very careful when there is only one staircase, because if you have only one staircase, we don't know that staircase, the flat or the horizontal portion is representing melting or boiling. So we must know, if we start with solid, then this thing will be melting. If we start with liquid, then this thing will be boiling. Alright, if we have two staircases, then it's quite obvious. The first one is melting, the second one would be boiling. Okay, now we must be able to predict all the states at a very specific region. Okay, for example, okay, if let's say we have a staircase like this, alright, so we know the first staircase is melting and the second staircase here is called boiling. Right, so we have a few regions. Let's call it, this is region A and B along the line, this is region B and C along the horizontal line, this is region C and D along the slanted line, this is D and E, and this is E and F, for example. So now I want to make a guess on what are the states. So this is the region and then this is the states. Alright, so this is A to B, this is B to C, C to D, D to E, and E to F. Alright, so we all must know, if we are on the slanted portions, okay, if we on the slanted portion, so on the slanted line, no matter the slanted line is going up, ascending, or going down, we only, but whenever we have horizontal line, okay, when we have horizontal line, alright, we always have two states. Alright, we always have two states in the horizontal line. The reason is, horizontal line, it's where the change of state is ongoing. I repeat, on the horizontal line, that is where change of state is ongoing. Alright, so that's why when the change of state is ongoing, we always have two states. For example, when melting is ongoing, so we might see some solid, we might see some liquid, and also accompany with some of the gases. Alright, so let's try to work on these questions. Alright, so this A to B is before the melting. So before you melt, A to B should be purely solid. Alright, B to C is on the horizontal portion. So this is the melting process. So from B to C, the melting process is ongoing. So when the melting process is ongoing, we might have some solid, and maybe some of the solid is already melted, become liquid. So we have solid, liquid. Alright, so do remember, along the horizontal line, we always have the mixture of two states. Alright, so when you come to C and D, this is right after melting. So when the substance fully melted along here, we should get liquids. There's no more solid already, because along here we are no longer on the horizontal line, so the melting process has fully completed. So now we go into D and E again. D and E is along the horizontal line. So for D and E, the boiling process is ongoing. So when the boiling process is ongoing, then some of the liquid might already become gases. Right? Lastly, for the E to F, this is the line, or this is the region that after the boiling. So you already finished boiling. So after you finish boiling, by right, everything should become gas. Okay? So on here, we have to understand that if, let's say, we are on the slanted portion, the steep line, okay, the slanted line, we always have one state. But on the horizontal line, we have two states. Alright? So this is what, okay, this is how we predict the states at a certain region. Alright? So now, we will try to look on the explanations for the heating curve. Alright, for heating curve, we have only two important explanations that we need to know. Alright, so for heating curve, alright, the exams questions will always ask us these two. Alright, first of all, we have to know somewhere here. Along the slanted region, we will realize the temperature is actually increases. Why? Alright, let's say we use a sample question. Why? Alright, the temperature it actually increases, alright, along the region A and B. Okay, so what happened here is this: when we want to do a melting or boiling process, when we have a heating curve, we are heating up our substance. So when we heat our substance, what happens is here is this. Let's say this is our particles. So we have a particles. Let's say the particle have some energy, 10 joules, for example. Alright. So the particles for heating curve, so the heat will be absorbed by all the particles. When particles absorb more heat, particles have more kinetic energy. For example, from 10 now it becomes 20. Alright. So when the particle has more kinetic energy, so the particle has, when the particle has more kinetic energy, the temperature will increases, because temperature is actually the measurements for the kinetic energy. Alright, so what happened here, we can write in this way. Okay, it's actually absorbed. Okay, all the heat is actually absorbed by our particles. Okay, all the heat is absorbed by our solid particles. So when the heat is absorbed by solid particles, so the kinetic energy is actually going up. So when we have more kinetic energy, temperature will always going up as well, because kinetic energy and temperature, they are directly proportional. Whatever thing change to kinetic energy, the temperature will do the same thing. This is why along A to B increases. because when we heat it up, all the energy come in, all the energy taken by the particles. When the particle become more energetic, the particle has higher kinetic energy, the temperature will go up. Alright, so this question is not being tested that frequent in the examination. Alright, in examination, this will be the popular question. So in examination, the question would be more keen to ask for the horizontal line. Okay, on the horizontal line, because we all must understand that when the change of state is ongoing, when the change of state is ongoing, for example, when melting, when boiling is ongoing, the temperature should be constant. The temperature doesn't change along the melting or boiling process, and we must know why. Alright, so the question asks why the temperature is actually remain constant, why we have a constant temperature during a melting process, or it can be a boiling. The answer will be the same. Alright, so the reason is very simple. So if we look in terms of the particles, alright, so the particles here, they have some of the force of attraction or some of the bond. Alright, so when we heat up the substance, all the heat is coming in, the heat is coming into the particles. Alright, so when we want to melt or boil a substance, we need to break the bonds. Okay, we break the bonds. So all the bonds are not going to be broken itself. So if we want to break the bonds are broken by heat. So all the heat come in is being used to break the bond. So none of the heat will go into the particles and increase the energy of particles. So the particles here, the energy still, right? The particle here, the energy doesn't change, unlike just now. Just now, because there is no bond to be broken yet, because we are not yet reaching the melting process. When the melting process is not yet reached, you don't need to break the bond. So all the heat come in, they don't need to be used to break the bond. All the heat can be directly taken by the particles. That's why the particle got more energy in the end, which increased in the temperature. But in this particular case, when we want to do a melting process, all the heat is needed and used to break the bonds between the solid particles. So when all the heat is being used somewhere here to break the particles, none of the heat will actually go into the particles. So your particle, the energy doesn't change, it's still 10. Alright, so when the energy of particle doesn't change, technically the temperature will not change as well. I have to write it in a form like this. Okay, so all the heat, alright, all the heat that go in, all the heat that absorb, alright, is actually used. Alright, we use all the heat to break the bond. We can use the word break the bond, or we can also use overcome force of attraction. All the heat is used to break the bond or overcome the force of attraction between the solid. Because do remember, to melt or boil a substance, we need to overcome the force of attraction. We need to break the bonds. So all the heat come in is used, okay, to break the bond. So when all the heat is used, none of the heat will go into the particles. So the kinetic energy of the particles doesn't change. Okay, the particles do not change in the kinetic energy. When kinetic energy doesn't change, temperature also doesn't change, or we call it constant. Alright, because temperature is highly dependent on the kinetic energy. Alright, so this is one of the very popular questions they can ask, alright, for the heating curve, alright, that we all must know. So let us try to do 1 or 2 questions about heating curve, alright, before we go on curve. Alright, so if we refer to the exercise booklet, we can refer to our page number 8. We can refer to page number 8. So for page number 8, we're going to look at question number 9. Diagram 3 is actually a graph of temperature versus time for heating of substance Q. Alright, so you look at this shape, this is a staircase, okay? We all see a staircase here. And then this staircase is going up when the temperature heating. So this is heating curve. If the temperature going down, that was a heating curve. Alright, so now, which statement is correct about the properties of substance X based on the graph? Okay, what is correct about this substance X? Alright, so now we will try to look at it. So first of all, the question is asking us which one is true. So the question say that substance X is a gas at room temperature. Don't know, because the question do not tell us starting state is a solid, liquid or gas. So we do not know that whether this is a melting process or it's a boiling process. So we not even know what process is happening. So it's very hard for us to predict whether this is a solid, liquid or gas at the room temperature. So this is wrong. Second answer say that physical change at 75 degrees Celsius, which is true. 75 degrees Celsius is along the horizontal line. When we are on the horizontal line, the substance are changing the states from one to another. Alright, so when they change the states, such as melting, such as boiling, the physical properties should change, which is true. Alright, anyway, let's see why C and donkey might be wrong. So for C, the question is that, alright, you are interval T1 to T2. This is T1, this is T2. No, this is a heating curve. For heating curve, no matter we are somewhere here or in the middle or even here, by right all the heat are being absorbed. Alright, for heating curve, in every single region the heat should be absorbed. Wrong. Lastly, alright, so they say that substance X is only in liquids at T1 and T2. Alright, so T1 and T2 is the horizontal line. On horizontal line, change of state is ongoing. When change of state is ongoing, we always have two states. Okay, we always have mixture of two states. For example, and liquid. For example, it might be liquid and gases. So you only have liquid. That is wrong. So the best answer would go for B. Okay. Okay. So now we will try to do one more questions. Alright, so this is a questions, alright, for heating curve in subjective. Alright, so question mentioned this. So this is the question. Question mentioned that diagram 1 show the setup apparatus to determine the melting point of substance X. So when we want to determine melting point, determine boiling point, we use heating curve. Alright, substance X is a white solid and substance X is electrical insulator. Alright, so this is the picture. Alright, so we will look at the questions. So first of all, alright, questions say that substance X melts at 61 degrees Celsius, which means the 61 degrees Celsius melting point. So now we all are requested to draw the arrangement of particle at 50. So how we're going to do? We can use the three-line methods to predict what is the states first. So this is the melting point MP, and this is the boiling point BP. So this is a solid, this is a liquid, and this is a gas. So question give us the melting point 61 degrees Celsius. The boiling point are not given, which is okay. So now we are looking at 50 degrees Celsius. According to number line, further than 61, so it should be somewhere here. So we know this thing should be a solid. Alright, so to draw solid in SPM, we all must fill up the whole boxes they give us. I repeat, in SPM, if we want to draw solid, we must fill up the box that they given, and we must follow a rules called 3 times 3, which means that you guys must draw minimum 3 row, and also which means that on the picture itself we must have minimum 9 circle. More is okay, but don't go lesser. Alright, in this case, if I draw 9 circle, also not appropriate because the whole box still quite empty. Right, for solid, the whole box should be filled up. So I just going to fill it up. Alright, so this is the arrangement for solid. Okay, they should be orderly, they should be together. Alright, so now we need to do the questions B. Question B say that we need to do a sketching. Question B requested us to sketch a graph of temperature against time. So when we see temperature against time, it must be either a heating curve or it's either a cooling curve. Alright, so now in this case substance, so it should be a heating curve. So heating curve, we all should know the shapes of heating curve should be a staircase. The question is that we have 1 staircase or 2 staircases in the diagram. So to answer the question, we just need to know whether the substance will melt or boil. Alright, so we want to heat the substance from room temperature become, so let's draw your axis, x and y axis. Your y axis would be temperature. Don't forget to label the units. The temperature is in degrees Celsius. And for the x-axis, we have time. So the time you can label in minutes or even in second. Let's say I label as minute. Alright. So remember, when you want to draw heating curve, you have to draw a staircase, and please be very careful with your starting temperature. The starting 0, when we want to conduct the heating curve, when we want to start heating at room temperature. So room temperature is 25, which is somewhere here. Alright, so when we heat from 25, alright, so our final temperature should reach 70. So before we reach 70, we will first reaching the melting point, 61. So at 61, it's ongoing, the melting is happening. So when melting is happening, you're going to see a horizontal line, because during melting or during boiling, we should always have a constant temperature. Alright, so after it melts, the temperature will go up again until it reaches the final temperature that we wanted, which is 71 degrees Celsius. In that case, but not 2, because the question never give a boiling point. So we don't know at 70 degrees Celsius whether the substance will boil or not. Alright, so this is how we draw a simple graph, okay, for our heating curve. Okay, so we will try to do another one more questions. Okay, so this is a questions in page number 9. Question number 10. So question saying that solid X is heated in a boiling tube, and the temperature is recorded at a regular time interval. So the melting point is 78 degrees Celsius. Which graph represent heating curve? So they wanted a heating. There's an important information here is melting point at 78 degrees Celsius. So first of all, we must be able to recognize the shapes of heating curve. Remember, heating curve temperature is going up, so we're going to see the staircase that going upward. So this is a staircase going upward, so we shortlist it. This is a staircase going downward, it's impossible. This is the staircase that going upward, it may be the answer. Case that going upward, then going downward, which is not the answer. Alright, so now we have answer A and C to choose. So what is the difference? Answer A has 2 staircases and answer C only have 1 staircase. So in this case, the question mentioned the melting point is 78. So if you melt at 78, so the answer A is not acceptable, because the 78 in the answer A is on the seconds. We have two staircases. The first staircase is melting, the second staircase is boiling. So by right, the 78 should refer to the boiling point. Alright, so for this one it's possible because the 78 is on a horizontal point. So when you only have one horizontal point, this horizontal point might be a melting or might be a boiling. Alright, so the answer C is acceptable. Alright, so now we're on the cooling curve. Alright, then we're going to do another few more questions. Alright, so now we're going to learn a little bit on the cooling curve. Okay, first of all, cooling curve. Alright, so cooling curve, the shape is always staircase. Alright, so this is the temperature on the y-axis, unit degree Celsius, and this is the time, unit maybe a seconds or maybe a minute. So cooling curve is also a staircase but going downward. So you can down, flat, down, flat, down. Alright, as usual, if we have two staircases, then it should be easy. If you have two staircases, we know that when you cool down something, alright, condensations always happen first. After condensation happen, then only we get into a process called freezing. Alright, so if we have two staircases, we know that the first horizontal line should be condensation, the second horizontal line should be freezing. If we have heating curve, our first horizontal line should be melting, and then our second horizontal line should be boiling. Alright, so you have to get this concept. Okay, so now if we only have one staircases, what if the question only give us one staircases? If we have one staircases during a cooling process, a cooling curve, then it might be condensation or it might be freezing. So in this case, what should we do? We're going to do the same thing like what we did for heating curve. So we have to know what are the initial states. What are the states that you begin with? If you begins with gas, you think in a way. If you begins with gas, you're cooling down the gas should undergo condensation first. But if you're starting with a liquid when you cool down, you should do freezing. Alright, so we have to be very, very careful when we only have one staircases. We have to really go and check what is the original or initial states that they give us. Alright, so as usual and similar as the heating curve, so you should able to analyze the curve. Alright, you should able to analyze the cooling curve. So the first analysis are very, very alike what you're going to see in the heating curve, which is the states. Alright, so if we know this is condensation and this is freezing, okay, so quite simple. In this region, condensation are not occur yet. So before you have condensation, this thing should be purely gas. Along this region, which is the horizontal line, condensation process is ongoing, in progress. So when condensation in progress, we might still have some gas coupled with some of the liquid that is being condensed. Alright, from this region, this is the region that after condensation. So after condensation completed, theoretically all the gas already become liquid. So at here we only have liquid. So on the second horizontal line, this is where the freezing is ongoing. So when the freezing is ongoing, we will have some liquid coupled with some of the solid. At here, this is right after the freezing. So this thing should be all pure solid already. So as you can see, this concept is very similar like what you see in the heating curve, whereby we learn that along the slanted line we only have one state, but on the horizontal line we always have two states. Alright, this concept is quite similar as what we're getting in the heating curve. Alright, so now when you come to cooling curve, alright, one of the most common question they like to ask us, is always the constant temperature. Okay, the question will always like to ask us the constant temperature we found out during condensation or freezing process. So again, this is a popular questions. All right, SPM always like to ask you something regarding the constant temperature. So this is a popular questions. So this is a popular question, so they will ask us this. So this is cooling curve. They love to ask somewhere here. They like to ask these horizontal portions, the constant. So the question might sound like this. Why, alright, why the temperature is actually constant? Why the temperature is actually constant during condensation states? Okay, during condensation, how come the temperature is constant? Because when we change from one state to the other state, for example, freezing, condensation, melting, boiling, you realize that the temperature is always constant. Alright, so how are we going to explain? So we might use some diagram to help us to imagine better. Alright, during condensation, what happened? The gas is become liquid. Alright, so gas. Alright, so this is the gas. Alright, they are far apart. So when you do cooling curve, the process of cooling will let you lose the heat. Okay, so the heat will actually be released to the surrounding. Alright, the heat. Okay, so what happened is that during condensation, we know that condensation change gas to liquid. If you want to change the gas to liquid, liquid and gas, there are difference in arrangement. So liquid should be more closely joined together. Alright, so when you want to change the gas to liquid, they need to bind, they need to bond together. So here they need to bond together. So over here, you realize that they are actually forming bond. Alright, so the gas is actually forming bond, or forming the force of attraction to bond, to bind together, so that the gas can become the. Alright, so what happens is that when you do cooling curve, the cooling process will release the heat to surrounding. But when you do condensation, condensation is forming the bond. So we all must understand a simple concept that we learned in PD3. Alright, so when we break the bond, we always need to absorb energy or heat. Meanwhile, if we are forming the bond, okay, if we are forming the bond, then it will release the energy, or so called it will release the heat. Alright, here, alright, what happened is that the bond is being formed between the gas. Okay, the bond is formed to pull all the gas together to form a liquid. So when you form the bond, you will release the energy. So the energy will come out from the bond. Alright, so when the energy come out from the bond, you will realize that for this particle, the energy that you lose to surrounding, alright, is balanced up, or is recovered by the energy you get when you form the bond. You can see over here, you lose some heat to surrounding, but at the same time, when you form, give the heat out, and the heat come into you again. Here is coming in, and here is going out. So when there is in and there is out, the heat doesn't change. So when the particles, their energy doesn't change, alright, so the temperature shouldn't change as well. Because do remember, temperature is highly dependent on kinetic energy. Alright, so I repeat one more time. Just assume this particle has 50 joule initially. So when you do the cooling process in the cooling curve, you release 10 joule to surrounding. So technically you should be 40 now. But don't forget that when you do condensation, you are forming the bond. When you form the bond, this bond will give the energy, will release the energy as well. This energy that released is surprisingly same as the energy you lost, which is 10 joule. So now the 10 joule is coming out from the bond. So when the energy coming out from the bond, this bond, the energy coming out from it, and you will come back into the particles. Alright, so just imagine to you, and 10 joule just now you loses to surrounding, 10 out and 10 in. Therefore, your particle still remain 50 joule. Your particle energy doesn't change at all. So when the kinetic energy of particle doesn't change, therefore the temperature will not change. So we can write in this way. Alright, we can write in this way. Okay. So during condensation process, the heat loss to surrounding, okay, the heat loss to surrounding, or during cooling process, exactly same as the heat release. Alright, heat loss to surrounding is same as the heat release during bond formation. Alright, so because the heat loss to surrounding is same as the heat release during bond formation, therefore you realize that the kinetic energy do not change. So when kinetic energy do not change, temperature will not change or constant. Alright, because again, like what I say, temperature is highly dependent on the kinetic energy. Alright, so we can do some questions on this. Alright, so we can continue with our question just now. Is on page number 10. Okay, is on page number 10. Alright, so this is a structured questions, okay, that we do some just now. We're going to continue it. Alright, temperature against time when liquid acetylene is cold. Alright, so you can see this is a staircase that going down, so obviously this is a cooling curve. Alright, so we have to be very careful with the states. When we only see one staircase, we know it might be freezing, it might also be condensation. So how we know it is either a freezing or condensation? So we must know what are the beginning states. Started with liquid. So when you begins with liquid over here, so when we have liquid, when the liquid first cooling down, by right, when the liquid cool down, you directly should go for freezing. No way the liquid will undergo condensation. So we are quite sure that this process is actually freezing. Okay. So now, the question asks us to determine the freezing point for acid. So freezing point. So all the change of states must occur along the horizontal line. We go and extend it, extrapolate it, you're going to get T2. So this T2 is the temperature when you do your freezing, which is what we call freezing point. So we just write T2. So please don't forget to write your units. The unit for temperature is degree Celsius. Alright. So the next question, popular questions. Alright. They're asking you how come the temperature did not change from B to C. Alright, how come during freezing the temperature doesn't change? Alright, so same thing, we can draw a picture to help us imagine freezing is actually changing some liquid particles. This is some liquid. We are trying to make the liquid become some of the solid. Alright, so as usual, when you do a curve, by right, the heat will actually lost to surrounding. Alright, the heat should lost to surround. But at the same time, when you do freezing, the liquids are adjoining together with the solid. So when liquid join with solid, you form bond. Formation of bond will release energy. So the energy will come out from the bond. Alright, and this energy that coming out from the bond is getting into our particles. So as you can see, the particle loses heat, and at the same time they got some on as well. Alright, so you have, so the energy is going out, at the same time some energy coming in as well. So when there's an in and out, the energy some sort like it cancel out. Alright, so when the energy cancel out, the kinetic energy of my particles doesn't change. When kinetic energy doesn't change, temperature will not change as well. So we can write in this way. Alright, during freezing, okay, during all the heat loss to the surrounding Alright, all the heat loss to surrounding is exactly same as the heat release during bond formation. Alright, all the heat going out to surrounding is same as the heat that we get during bond formation. Okay, the energy going out is same as the energy we get when we form a bond. So by doing this, the kinetic energy alright, so when kinetic energy do not change, you will realize that the temperature will not change as well, because again, kinetic energy is highly dependent on the temperature is highly dependent on kinetic energy. Alright, so heating and cooling curve might be a bit technical compared to other subtopics, okay, because it involves some good explanation. You must be able to identify the shapes of heating curve, of the cooling curve, which is staircase. Alright, you must able to know what are the states. Remember, along the slanted line, alright, so we only have one state. Along the horizontal line, we have always two states. Alright, and we must be able to explain why the temperature is constant for the heating curve, alright, and why the cooling curve. Alright, so these will be always tested, okay, in the examination. Alright, so for now, if we look at the objective, alright, if we look at the objective, we should already know the heating curve and also the cooling curve. Okay, so for next on, we'll try to discuss the scientists who contribute to the development of the atomic structure. Alright, so there are total 5 scientists who make a major contributions for the development of atomic structure. So for this particular part, normally the questions will be tested in objective most of the time. Alright, so one of the simplest way for us to memorize the name along with their contribution is actually like this. Okay, so we can try to memorize a simple sentence or an acronym, okay, alright, which is called don't throw rubbish, okay, below carpet. Alright, don't throw rubbish below carpet. Okay, save Earth, protect Mother Nature. Alright, so the sentence will be don't throw rubbish below carpet, save Earth, protect Mother Nature. So how does this sentence related with the scientists that contribute to the atomic structure? So we will first take out the first letter on each of the words, right? And we create some keywords. The word D stands for Dalton, all right, John Dalton. The T is Thomson, J.J. Thomson. The R is Rutherford, okay. The word B stands for Neil Bohr. And the last one, the C, is James Chadwick. So we don't need to know names of these scientists because normally this thing is being tested in objective. So as long as we know part of the name should be more than enough. Alright. So the word S stands for sphere. Alright. The word E stands for electron. The word P stands for proton. The word M stands for moving. And last one, the N stands for neutron. Alright, so Dalton proposed that atom is a sphere. J.J. Thomson discovered electron. Ernest Rutherford, Neil Bohr found that electron is not stagnant, electron is actually moving. James Chadwick discovered neutron. So this is one of the very simplified way for us to memorize the scientists along with their major contribution. Alright, so we will try to do 2 to 3 questions on this. So you can turn to page 11. Alright, turn to page 11 in the exercise booklet. So here's the question. Alright, so we're trying to do these three questions together, so they are related with this. So the first question, who discovered neutron? So if you look at our case, alright, neutron is discovered by Chadwick, alright, so it should be James Chadwick. So the questions will be very straightforward. It's not going to be tricky, very straightforward and direct. Okay, so the next question is SPM 2016. Alright, so the question gives you a model of atoms as usual. Alright, please make introduction to this particular model. Right, let's look at the picture. So for this picture, we can see that this thing is labeled as electron. The electron is moving outside the nucleus. In the middle, there is a nucleus, and then the nucleus only contains proton. Alright, so when the question mentioned electron is moved, electron moving, so electron moving, it should be proposed by Niels Bohr. Alright, so our best answer would go for, alright, next one. Okay, so now this is another part. This will be a bit older. This is SPM 2005. So the question show you a model of an atoms. So the question asks, who actually introduced this particular model? Who introduced this model? So as we can see, there are nucleus in the middle, alright, and outside here there are some electrons. The electron is moving in the orbits. Okay, electron is moving in their orbit. The one who proposed electron moving should be Niels Bohr. So we will go for Niels Bohr. Alright, so as you can see, these concepts are not very hard. As long as you can memorize in the easy way, the questions shouldn't be too hard to be solved. Because when they come to the scientists, the questions normally are very straightforward. Okay. Summary. Okay, we will make a quick summary of all these things about proton and also electron. Okay. So there are many students always confused between the word particles, alright, and also subatomic particles. Alright, so when the question say particles, we are actually talking on atoms, which is something who come alone. It can be a molecule. Molecule is a non-metal gang. Non-metal and non-metal are joining together. Meanwhile, ion. Ion is anything that got charged, okay, or anything that made from metal and non-metal. Alright, so this is particles. Please do not mess up particles with subatomic particle. The word subatomic particle, the word sub means something smaller. So there are some particles even smaller than the atom. There are some particles smaller than atom. That's what we call subatom. They are the particles that found inside the atom. So right, this is something we found inside the atom. So when we see the word subatomic particle, by right, that's across our mind. So they can be a proton, they can be a neutron, and they can be electron. So this is the concept that we must know. Alright, so for proton, neutron, electron, you have to know some of their comparison. For example, first of all, we need to know the locations. Alright, where we can find proton. Proton is found at the center of the atom, which is called nucleus. Neutron is also found at the center, nucleus. Electron is actually found out nucleus. Alright, and the electron is actually moving in the orbitals. Alright, or we also can call shell, that is outside the nucleus. Alright, so we can draw a simple picture, a simplified picture like this. Okay, we can assume that, alright, this is the center of the atoms. This thing is called nucleus. Alright, in the nucleus, it contains proton and also neutron. Alright, all the electron is outside the nucleus and they're moving in their orbitals. So the orbitals can be drawn in a circle with different radius. Okay, and the electron is actually moving inside here. For example, this is the electron. Okay, this is the electron. Like this is the electron that moving in the orbitals. Alright, so we also need to know what are the relative charge, what are the charge. Alright, so each of the proton is carry positive 1. So neutron, each of the neutron carry the charge 0 because neutron stand for neutral. So electron, every single electron carry the charge of negative 1. Okay, afterward we also need to know the mass. Okay, so the mass of nucleus, the mass of proton is 1. Alright, so the mass of neutron is also 1. In the other word, proton and neutron, the mass is the same. Alright, electron, the mass is 1 over 1836. Alright, which we can assume to be 0. Okay, the mass of electron are so light in compared to the proton and also neutron. That's why the negligible. Okay, we can assume that the mass of electron is equivalent to 0. Okay, so this is what we need to know about the subatomic particles, the proton, neutron and electron. Okay, make sure we understand the locations where we can find all these subatomic particles, what are their relative charge, and also what are their relative masses. Okay, alright, so the next thing that we can discuss is on this one. Okay, so after we understand the scientists who contributing to the development of the atomic structures, the next thing that we have to understand is called standard representation. So this is a very important concept because we're going to see this concept quite frequent in our chapter 4 and also chapter 5. Alright, so first of all we have to understand representation. What is standard representation actually? Alright, so let's look at the screen. So standard representation, okay, standard representation is actually one of the way or one of the format. Okay, this is the format for us to represent an elements. Alright, this is the format that we use to represent an elements, especially when we talk about periodic table. So in periodic table, all the elements are represented in a standardized format. This format is called standard representation. Okay, the format normally accompany with this. We're gonna have a very big symbol. Alright, this big thing is actually the symbol of the chemicals. And here normally we have two numbers on the left. Alright, we have two numbers on the left. So this number, one is called A, one is called Z. So you don't need to memorize this letter. This letter is not important because this is just a general representation. You just need to know how to analyze will do. Okay, I give you a simple example. I give you a simple example. Let's say we have a sodium with a number 23 and 11. All these numbers no need to be memorized because all these numbers will be given. See that this big thing is actually the symbol of our chemical. So Na is a symbol for sodium. Alright, as you can see, we always have two numbers here. And you always see a big number as the top. Okay, you always see a big number on top, and you're going to see a small number at the bottom. The sequence will not change in the SPM. Alright, so this big number has a name. This big number, we call it as nucleon number. We call it as nucleon number. Please be careful, it's called nucleon. It's not neutron. Okay, this small number is called proton number. So these two numbers actually tell you and give you some idea what it is all about. Proton number, as the name indicate, this number will tell you the amount or the number of proton that you have in the nucleus. Alright, how many proton that we found in nucleus. This big number, meanwhile, is called nucleon number, which is the sum, okay, or which is the total of proton and also neutron. Okay, you have proton and neutron. Okay, it's a total number of proton and also neutron. Okay, all right. So So this 23 means that we have proton and neutron mixed on together. There are total 23 of them. Alright? So, what is the purpose? What is the purpose for us to learn standard representation? Alright? So, for standard representation, every time when we were given a standard representation, we are always able to do this, okay? We will always be to extract. We will always be able to extract three infos, okay? We always be able to extract three informations from a standard representation. So whenever we have a standard representation, there are three informations that we can extract. The first information is that we will know how many protons is there. We also electron is there. Alright? So I'll run through quickly and we will use some exercise for demonstrations on how this thing works. Alright? So for the standard representations, alright, what you need to know is this. The number of proton, you can always refer to the proton number. The proton number can directly tell us how many protons we have. Alright? For number of big number, which is the nucleon, go to minus the small number. So when you take the big number minus small number, you will get the neutron. So number of electron is a bit special. We will use a few examples for demonstration. Okay? I will use a few examples to demonstrate so that we can get a better idea how this thing works. Alright? So now we will try to work on a few right? So I give you three examples here perhaps. Okay? The first example is this. Okay, let's start with the one that we have just now, alright, which is the sodium. Alright. So example number 1, let's say we have sodium. So sodium is given 23 and 11, so you know it's not very hard. So to find the proton, just take the small number, so which is 11. To take a neutron, you just need to take a big number minus small number, so 23 minus 11, so we're going to get 12 neutron. Lastly, we have to be very, very careful with electrons. Okay. Electrons can differ quite some, depends on condition. Alright, so the first statement we need to know is this. If our atoms is actually neutral, if we have a neutral atoms, so the number of proton must be exactly equal to the number of electron. Okay, number of proton must be always equal to number of electron, provided it is neutral. Okay, so now in this case, alright, so how many electrons we have? So we look at the substance. This substance is neutral because we don't see any charge in this particular symbol. So when this is neutral, the number of proton and electron must be the same, which is 11. Alright, why they must be the same? Because we learned moment ago. Alright, every proton, the charge positive 1. Every electron, the charge is negative 1. So you see, if let's say my particle got 11 proton, my particle has 11 proton. So the total charge would be positive 11. If my particle has 11 electron, the total charge will be negative 11. So positive 11 minus negative 11, so the total charge, the net charge is actually 0. And this is what makes it neutral. Alright, so for a substance to be neutral, the positive and negative charge must cancel out. To do that, the number of electrons must be the same. Alright, so the things will get tricky when the charge start to kicks in. So when we have charge, so the whole things might be a bit trickier. Okay, so I'll show you two examples when the charge kicks in. So let's look at our example number 2. So example number 2, you are given a K, which is a potassium. This is 39 and this is 19. Alright, so here there is a plus on top. Alright, so there are two ways to solve these questions. So listen, there are two different methods to solve this question. One of the simplest method is this. Okay, as usual, to find proton, just copy the proton number, which is 19. Alright, to find neutron, just use the big number minus the small number. So you got 20. Alright? So to get electrons, we have to be very, very careful. So in this case, the electron cannot be 19. It cannot be same as proton because you have charge. Alright? Remember, proton and electron is only same in terms of amount if and only if they are neutral. Alright? So in this case, we have charge. So when we have charge, the electron will not same as proton. Okay, so one of the way to solve the question is this. When we see positive ion, positive means that you are donating electron. Negative means that you are receiving electron. Okay, so when we see positive ion, means that the electrons are being donated. Alright, when we see negative ion, it means that the electron is actually being received. Okay, so when we see positive, no number means 1, means that this guy is actually donating 1 electron. So if you have 19, you donated 1 electron, should become 18. Alright, so this is one of the way. Okay, so if we don't want to do this method, there's another alternative method as well. So another alternative method we can do is this. Alright, so this is another alternative method. So for the alternative, we can do something like this. Alright, so we want to look at the total charge of these questions. The total charge of this question is positive 1. Alright, and we have to ask ourselves, who actually contribute to the charge of our particles? So in the particles, we have proton, we have neutron, we have electron, but only proton and electron, they have charge. Neutron is neutral. So proton we know is 19. So we know every proton the charge is positive 1. So 19 proton will be positive 19. Electron, I don't know, question mark over here. So but I know electron carry the charge negative. From a mathematical perspective, 19 need to minus a number, will get positive 1. So 19 has to minus 18. Then only you can get the charge of positive 1. So which means that we have 18 electrons. Alright, so this is also an alternative method for us to solve the questions. Right, we can try to do one more example before we do some exercises. Alright, so the next one we have to know. Okay, let's look on our example 3. So for example number 3, alright, let's say we are given a sulfur, right, which is 32, 16, and the charge is 2, negative. Alright, so as usual, let's look at our proton. Proton, we can refer to proton number, which is 16. Neutron, we all can take a big number minus small number, so 32 minus 16, so you get 16. Okay, last one is electron. So we have to be very careful with electron. So electron shouldn't be 16 because this particle is not neutral. Alright, so there are two ways to solve the question, just like the example 2 that we discussed a moment ago. When you see negative charge, 2 negative, when you see negative charge means that okay, the electron are being received. Okay, so since we see 2 negative here, means that you receive 2 electron. So when you have 16, you receive additional 2 electron, you will get 18. This is how you predict the amount of electron. Again, if this method is too hard for you, you can use an alternative method. So the alternative method is like this. Alright, so we know that this particle in the end, the total charge has to be negative 2, okay, as per show on here. So and then we know only proton and electron can give us the charge. Alright, so for the proton, okay, we all know the amount is 16. Every proton, the charge is positive 1, so we have positive 16 as a total. Electron, I'm not sure about the amount at the moment, but I know electron carry charge negative. So from a mathematical perspective, positive 16 need to minus with an unknown number to get negative 2. So positive 16 has to minus 18. Then only we can get the total charge negative 2. By doing this, we will know the total charge is actually negative 2. So now, let us try to learn another one more concept, then we will use and combine all these ideas to do some questions together. Alright? Next things that we need to know is called electron arrangement. Alright, the next thing we have to know is called electron arrangement. Okay. So as what we learn, electron, they are not stagnant. We all know that electron is actually moving, and the electron is actually staying in their own shell, or we call it as orbital. Alright, all the electron is moved in their own shell or orbital. For example, this is the nucleus, and then outside here, all these circles is actually what we call orbitals, or we call it as shell. So every shell has a maximum number of electrons they can hold. Okay, all right. So every shell, they have a maximum number of electrons they can hold in. All right. So this is the shell number, and then this is the maximum number of electron. So we have shell number 1, shell number 2, shell number 3, and shell number 4 for demonstrations. Alright, because in SPM normally we're not going beyond 4 shell. Okay, shell number 1 is the shell that is closest to the nucleus. Alright, when the shell is closer to the nucleus, the shell number is smaller. The first shell, the first circle can only put 2 electron maximum. The second shell can put maximum 8. The third shell also can put maximum 8. Shell also can put maximum 8. Alright. So for SPM, our focus is more on the number 2 and number 8 only. Alright. If we somehow see some arrangement like 18s, okay, 32, so they are not part of the syllabus that will be tested in SPM. Okay, for SPM, when it comes to electron arrangement, you just need to make sure that you understand 2 magic number, which is 2 and 8. So first circle can put 2 electrons only. The second circle and onward all can put up to 8 electrons. Okay, so now we will try to do some questions on this. For example, let's say we'll try to do 2 examples here. So let's say we have a sodium 23 and 11. So the question wants us to go and write the electron arrangement. So when we want to write electron arrangement, we must know the amount of electron. Do remember, when a particle is neutral, the amount of electron is exactly same as the proton. So I know the sodium has 11 proton and therefore 11 electrons. So when we have 11 electrons, you can write the whole thing as 2, 8, and 1. Alright? Because the first circle can put 2 electron maximum, the second circle can put 8 maximum, this one can put only 1. So when you add together, the total number should become 11. Alright? So you must make sure you know how to write this electron arrangement. This is one of the basics knowledge that we need to know in chemistry. And do remember the amount of electron at the outermost shell. Okay, the amount of electron at the outermost shell is called valence electron. Okay, it's called valence electron. So as long as we know how many electrons are there in the outermost shell, all right, the shell that is furthest away from the nucleus, then we will know the amount of valence. All right, so let me show you one more example that it can be a little bit trickier. Okay, so for example, let's say we have a substance called oxygen, O, right, which is 16 and 8, and this is 2 minus. Same thing, you have to be very careful when the charge kicks in. So now I want to write the electron arrangement. Usual, the electron arrangement, okay, first of all we have to know the amount of electron. Oxygen proton number is 8. You will only have 8 electron if and only if the oxygen is neutral. But in this case, the oxygen is not neutral. Oxygen carry negative charge. So when we carry negative charge means that we receive electron. 2 negative means you receive 2 additional electrons, you make it become 10. So once we know we have 10 electrons, we can make our arrangement, which is 2 and 8. Alright? So in this case, we have 8 valence electron. Okay? Alright. Valence electron is very important, especially when you're dealing with your Form 4 Chapter 4 periodic table. So for now, I just need you to know that, alright, for all the substance, if they have same number of valence electron, if the substance have the same number of valence electron, they will have exactly the same chemical properties. They will have exactly the same chemical reaction. Alright, same valence electron, same chemical properties. Example, substance A is 2.1. For example, substance B is 2.881. Substance A got 1 outer electron, substance B also have 1 outer electron. So both of them have same number of valence electron, therefore they have exactly same chemical properties. Alright, whatever reaction A can undergo, B should be also able to do the similar thing. Alright, so this is what we, so now let us put everything that we have learned into practice. Okay, let us put everything that we have learned into practice. We will do about 3 to 4 exercises together, alright, before we cover the last part for your chapter 2. Alright, so now you can refer to the page 11 in the exercise booklet. Okay, you can refer to the page 11 in the exercise booklet. Okay, it's page 11 in exercise booklet. So for page 11, alright, so you can see question 15. So question 15 gives us a standard question, asks which of the following is the electron arrangement and the neutron. Alright, so electron arrangement, we just need to know the amount of electron. Amount of electron always same as amount of proton if and only if the substance is neutral. So for this particle, we don't see any charge over here, so it's neutral. So when it's neutral, okay, when this particle is neutral, so we know that the amount of proton same as the amount of electron. So we have, so when we have 11 electron, arrangement should be 2, 8 and 1. Quite straightforward. So our answer might be A or might be C. So now we need to counter check the next thing, which is the number of neutron. So we learned a moment ago, to find the neutron, just get big number minus smaller number. So 23 minus off with 11, you're going to get 12. So best answer go for C. Alright, trick is not to say very tricky, it's very straightforward. Most important to understand how does this concept works. Alright, so now we can turn on to page number 12. Alright, turn on to page number 12. Right, page number 12, we have 3 more questions to discuss here. These 3 questions can go a little bit more complicated. Okay, alright. So the first one, table number 3 shows the proton number for elements U, W, and element Z. Alright, so the question asks which particle has the same of electron. So we have to be very careful with electron. So for U is neutral, so the electron should be exactly same as the proton, which is 8. For V is also neutral, no charge, the electron same as the proton, so which is 9. So the amount is not the same, so it's not the answer. For W is neutral, so it's 10. For Z, we have 11 protons, neutral, so we also have 11 electrons. Alright, now we have to be careful with C and donkey, because C and donkey we see that the charge start to kick in. So start with W. W is neutral, so the number of electrons same as the proton, which is 10. For V theoretically, if you have 9 proton, you should have 9 electron, but do a charge of -1. So when you have charge, means that your electron shouldn't be the same. So when we see negative charge, we know that we are receiving electron. -1 means that we are receiving 1. So 9 plus 1, we're going to get 10. So we have 10 electron for W and 10 electron for V. So the answer go for C. Alright, so you all have to be very careful when you see the charge. Alright, the next question has tested us a bit on the critical thinking. You can call it a K-part. Alright, so this is question 17. Diagram number 6 show you the electron arrangement for J3 plus ion. So you have an ion which is J3 plus. So they give us the neutron number of 12. We have neutron 12. So now they ask us about nucleon number. Okay, let's try to think about if we want to get a nucleon number, we know the nucleon number is, alright, or is the total of actually proton and also neutron. Okay, we know that is actually the nucleon number is the sum of proton and neutron. So we already given the number of neutron. So which means that we only need to go, alright. So to find the number of protons, we can use one of the alternative method used just now. Alright, we can do something like this. Alright, the total charge is positive 3. So total charge is actually positive 3. Who can contribute to the charge in an atom? It must be proton and electron. So in this case, we don't know the amount of proton. I don't know, so I put a question mark. And then, but I know the charge of proton is positive. Electrons, the amount I know from the picture. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 electrons. And every electron, the charge is negative. Alright, so mathematics, unknown number minus 10 to get positive 3. So this unknown number, alright, we must have 13 proton. So now we already know our number. So now our proton amount is 13 and our neutron number is given is 12. So when we add proton and neutron, we get 25, which is the nucleon number. So the nucleon number is 25. So for the questions 18, you test on it, you can try to work on it also, alright? Because for question 18, the concepts are very similar as the questions 17 as well, alright? So you are given the number of neutrons, they want to get nucleon number, so you need to use this method to find out the amount of proton. You just sum it with the amount of neutron, you will get nucleon. So this one, you can try to work on it yourself, alright? So now, we have already come toward the end of this entire chapter, alright? So the last thing that we need to learn in this chapter would be a concept which is isotopes, alright? So the last concept we need to learn is called isotopes, alright? Okay, so the last concept that we will discuss for the chapter 2 atomic structure is called the concept of isotopes. So first of all, we have to understand what is isotope. Isotope is atom. Alright, isotope is an atom of the same element. Alright, isotope is the atoms of the same element which they have same proton number. Alright, they have same proton number, but they have different nucleon number. Alright, different nucleon number, or you can say different number of neutron. Alright, in short, anything have same number of proton but different number of nucleon or neutron, that is called isotopes. Okay, let's learn by an example. So we have a carbon like this. So we have a carbon. So this is what we call carbon 12. And this is what we call carbon 14. Whenever we see a chemicals come along with a number, that number will be their nuclear number. Alright? Carbon 14. So we can compare. So both of these carbon have exactly same number of proton. They have 6 proton. But you can see that the number of nucleon are different. So one have 12 nucleon and one have 14. Alright? apart from the nucleon number being different, the number of neutron also different. Okay, we learned a moment ago, to find the number of neutron, you just need to take a big number minus small number. So 12 minus 6, you have 6 neutron for this case. And then 14 minus 6, we have 8 neutrons for this case. So we can see that the number of neutron also different. So we have same proton number, but we have different nucleon or different neutron. Okay, so this is what we need to know about isotopes. Alright, so for isotopes, what you need to know is this. So all the isotopes, okay, the properties, you have to focus a bit on properties. So isotopes, they will have different physical properties. Different physical properties as in they might have different colors, they might have different melting point, boiling point, right? That. But all the isotopes have exactly same chemical properties. Okay, what it means by same chemical properties, all isotope, for example, if carbon 12 able to burn in oxygen, carbon 14 also able to do the same. They can undergo the same chemical reaction. Why? We learned a moment ago, chemical properties is always affected by valence electron. So when these two carbon have same number of electrons, is 2.4. So both of them will have 4 valence electron. When you have 4 valence electron for both, when you have same valence electron, so their chemical properties should be the same. Alright, they have same number of valence electron. Okay, so this is one of the concepts that we need to know. Alright, so the last thing that we will learn, alright, for isotope is that we have to know some of the usage of isotopes. Alright, isotopes out there, alright, for SPM, you just need to know what are the isotopes that you need to focus. Alright, isotope is very useful in our daily life in different industry. So we have to know some of the usage of isotopes. There is a long list of isotopes in the reference book or textbook, which we don't need to memorize all of them. So for isotopes, we just need to focus on a few. The most important isotope that all of us must know is called carbon-14. We must know. The second isotope that we need to know is called cobalt-60. These two isotopes, it's very popular and we must know their usage when it comes to SPM. Alright, so of course we have some other things such as sodium-24. Alright, we also have isotopes which is called iodine-131. We also have isotopes called uranium-235. But these three isotopes, they are less important, alright, because it's not being tested that frequent in examination. Alright, so if you can memorize all the 5 isotopes listed in on the screen and also the usage, that will be very good. But if you couldn't memorize all of them, you just need to make sure that you try your level best to memorize the first 2. So for carbon-14, the usage is that we the age of fossils, alright, and also artifacts, alright. So when we have fossils and artifacts, we want to know like how these fossils and artifacts was last for how long already, for how many years already, so we can use carbon-14 to do it, alright. Cobalt-60 has 2 functions. We can use it in the food industry as well as we can use it in the medical industry. In food industry, cobalt-60 used to kill bacteria. In the medical industry, cobalt-60 used to kill cancer cell. Alright. Sodium-24, meanwhile, is used to our underground pipe leakage. Okay, so if there's any pipe leakage underneath, alright, so we can use sodium-24 to do the detection. So iodine-131 is always used to detect as well as used to treat, okay, thyroid disease. Alright, so if there is a thyroid disease, we can use the iodine-131 to do. Last one, uranium-235. Uranium-235, it's used as or used in the nuclear plant. All right, we use uranium-235 to generate power. All right. So these are all the isotopes. Do remember, the most important that you must, the one that you compulsory to know, it's carbon-14 and cobalt-60. So let us turn to page 13 and get it done with the chapter 2. So this is your exercise booklet. This is page 13. We will discuss together. So the first question is asking, which of the following are the differences of isotopes? So what are the difference between isotopes? Isotope, the number of protons don't have difference. They have same number of protons, so it's wrong. Isotopes have different number of neutrons. That's true. All right. Isotopes have different physical properties. That's true. All right. So the melting point, the boiling point, the colors might be different for different isotopes. Last one is the chemical properties. Chemical or chemical reaction should be the same for the isotope, because all isotopes have same number of proton, so the number of electrons should be the same. So when they have same number of electron, the number of valence electron would be the same as well. So the chemical property should be the same, no difference. So the answer go for 2 and 3, which is C. Alright. So the next one, question 20, right? This is SPM 2015. Right? Biologists intends to destroy bacteria that cause potatoes to rot using radioisotopes. Which of the following suitable to use? The keyword here is food and also bacteria. So if we want to use in food industry, if you want to destroy bacteria, it has to be cobalt-60. All right. So the last one, this is a subjective question that came out last year, SPM 2017. So question say, representation of two isotopes of carbon. So we have carbon-12 and carbon-14, same like the example that we discussed a moment ago. First of all, we have to give the meaning or so-called the definitions of isotopes. So isotope is actually defined as atom of the same element. Okay, isotope is the atom of same element with same number of proton or same proton number, but you have different nucleon number. If you don't want to write different nucleon number, you also allowed to write different number of neutrons. So both answers are acceptable. Alright, please do not write neutron number. Okay, there's no such thing called neutron number. It is nucleon number. Alright, so now same thing over here. For the next question, we need to use the standard representation to find out the electrons and also neutron, which shouldn't be too hard. Particle has no charge, it's neutral. Neutral particles, electron same as proton, so 6. Same as carbon-14, you have 6 proton, therefore 6 electron because it is neutral. To find neutron, just take big number minus small number, so you got 6. 14 minus 6, you got 8. So that's how you score 2 marks easily. So last one, you are requested to give and suggest a usage of carbon. This is 14 in our daily life. So as what we learned just now, carbon is one of the most important isotopes they always test us. Okay, carbon-14 can use to detect the age of fossil and artifacts. Okay, it can help to determine the age of fossil and also artifacts. Or you can say that carbon-14 is used in archaeology, also can. Alright, and that's the end of the. So when you do the revision, you always can refer to the checklist. Okay, you can always refer to the checklist so that you know what are the expected outcome that we need to know for a chapter. Alright, so this will help you to understand whether or do you miss out any concepts in that entire chapter. Alright.